You woke up this morning and something felt off. Not in a dramatic way, not in a way that demands immediate attention, but in a quiet, persistent way. Your knee spoke before you stood. Your lower back registered its complaint before you even moved. Your body felt slightly heavier than you remember it being, and your eyes, they carried a weight that sleep did not fully remove. Not exhaustion, something deeper, something cumulative. And here is the part most people never say clearly. You are not imagining this. You are not exaggerating it. And you are almost certainly not as old as your body is currently behaving. Let that settle. There is a number on your birth certificate. That is your chronological age, a simple count of time. The number of years the Earth has circled the sun since you arrived. But there is another number, a hidden one, your biological age, the age of your cells, your mitochondria, your tissues, your immune system, your inflammatory baseline. And these two numbers rarely match. For many people today, biological age is accelerating ahead of chronological age, meaning the body is aging faster than time alone would suggest. And most people only notice it when the gap becomes physical. This is not a wellness message. This is not about hydration or habits. This is about the underlying system, the cellular, thermodynamic, and biological machinery that determines how old your body actually is and where exactly that machinery begins to fail. Because the answer is not what most people think. It is not simply stress. It is not simply diet. It is something more fundamental. It is physics. It is information theory. It is the second law of thermodynamics operating inside every cell of your body right now. And once you understand that, what you feel in your body becomes explainable. Here is the foundation. Entropy. The second law of thermodynamics states that in any closed system, disorder increases over time unless energy is continuously applied to maintain order. Order is not natural. It must be maintained. Life appears to resist this law, but it does not escape it. It pays for resistance with energy. Constantly, every heartbeat, every breath, every repair process, every cellular function. All of it is energy spent against disorder. And here is the key point. When energy supply falls behind demand, when repair systems slow, when damage accumulates faster than recovery, entropy advances. Quietly, systematically. And what you experience is not abstract decline. It is physical reality. That stiffness when you wake up, that heaviness in movement, that sense your body is slightly older than it should be. Now focus here. Press your thumb into the back of your opposite hand. Notice the skin, its resistance, its return. What you are feeling is a collagen matrix, the structural protein network that holds together skin, joints, cartilage, and connective tissue. And over time, that structure changes through glycation. Glucose molecules bind to proteins. Over time, these bonds create cross-links, rigid structures that accumulate in tissue. The result is stiffness, reduced elasticity, slower recovery of shape and movement, skin that rebounds less quickly, joints that move less smoothly, arteries that lose flexibility. This is not metaphor. This is chemistry. This is physical change in biological material. But glycation is only one layer. To go deeper, you enter the cell, specifically the mitochondria. Mitochondria produce ATP, the energy currency that powers every function in the body. No ATP, no movement, no repair, no cognition, no immunity. Everything depends on it. And mitochondria carry an ancient origin. They are descendants of bacteria that lived independently billions of years ago, later absorbed into early cells in a symbiotic relationship. They still carry their own DNA, their own replication system, and they are highly sensitive to stress. Under sustained demand, mitochondria produce energy through oxidative phosphorylation, which also generates reactive oxygen species. Free radicals, unstable molecules that damage proteins, lipids, and mitochondrial DNA. Cells normally neutralize them using antioxidant systems like superoxide dismutase, catalase, and glutathione peroxidase. But under chronic stress, this balance breaks. Reactive oxygen species accumulate faster than they are cleared. Damage builds. Mitochondrial efficiency declines. ATP production drops. And when ATP drops, every system in the body begins to slow. Muscles recover more slowly. The brain processes less efficiently under load. The immune system becomes less precise. And the subjective result is fatigue. Not normal tiredness, but systemic energy limitation, a body operating below its optimal capacity. And here is the key point. You are not lazy. You are not weak. You are not undisciplined. You are experiencing a biological energy. In 1936, a Hungarian-Canadian endocrinologist named Hans Selye conducted a series of experiments that would fundamentally reshape how we understand stress in living systems. He placed laboratory rats under controlled physiological stress through cold exposure, forced exercise, and surgical trauma. What he observed, consistently across every variation, was not random breakdown but a structured biological response. The adrenal glands enlarged, the thymus and lymph nodes atrophied, and gastric ulcers developed. Most significantly, the body's internal resource allocation shifted dramatically away from long-term maintenance functions and toward immediate survival functions. Selye called this pattern the general adaptation syndrome, describing 3 stages: alarm, resistance, and exhaustion, and in doing so, identified a biological system designed for short-term crisis that was being forced to operate continuously and gradually breaking under the load. That same system is operating inside you right now. At the center of this system is cortisol, a glucocorticoid hormone secreted by the adrenal cortex and regulated through the hypothalamic pituitary adrenal axis. Under acute stress, cortisol is highly adaptive. It raises blood glucose to fuel immediate energy demands, suppresses non-essential systems to redirect resources, and sharpens attention and focus for survival. The issue is not cortisol itself, but its persistence, because the HPA axis cannot distinguish between a predator in the wild and a notification on a screen, between physical danger and social evaluation, or between immediate threat and anticipated threat. It only detects signals of pressure, and it responds the same way each time. In modern life, those signals are constant notifications upon waking, urgent emails, social comparison embedded in digital platforms, financial uncertainty, and a news cycle engineered to sustain attention and alertness. Individually, they are not catastrophic, but collectively, they are continuous, creating chronic cortisol elevation that reshapes biology over time. Chronic cortisol exposure suppresses immune function, not in an immediately noticeable way, but in a systemic one that reduces the body's ability to surveil abnormal cell activity, regulate inflammation, and maintain protective mucosal barriers in the gut, lungs, and sinuses. It suppresses collagen synthesis, compounding structural decline in connective tissue, already affected by other processes like glycation. It also affects the brain, particularly the hippocampus, the region responsible for memory consolidation and spatial navigation, where chronic stress has been associated with measurable reductions in volume. Beyond the brain, it disrupts gut motility and permeability, alters microbiome balance, interferes with insulin sensitivity, and creates a metabolic environment that accelerates glycation. At the hormonal level, it suppresses anabolic systems such as testosterone, estrogen, human growth hormone, and IGF-1, all of which are essential for repair and regeneration. Cortisol and growth hormone operate on opposite sides of a metabolic balance. When cortisol remains elevated, growth hormone declines, and with it the body's capacity for protein synthesis, mitochondrial biogenesis, and autophagy, the core processes of cellular repair. This is where inflammation becomes central, because it links stress physiology to systemic aging. Acute inflammation is a precise and essential repair mechanism that isolates damage, recruits immune cells, and accelerates healing in a controlled and self-limiting way. Chronic low-grade inflammation, however, is a persistent activation of the same system without resolution, characterized by elevated inflammatory cytokines such as interleukin, 6, TNF-alpha, and C-reactive protein. Over time, this sustained immune activation damages blood vessels, promotes plaque formation, degrades joint cartilage, and disrupts neural function through microglial activation in the brain. It also increases intestinal permeability, allowing bacterial fragments like lipopolysaccharides to enter circulation and further amplify immune response, creating a self-reinforcing cycle of inflammation. This state does not resemble an acute illness, but rather a slow, systemic degradation, similar to a building where a fire suppression system continues running long after the fire is gone, gradually causing structural damage through constant exposure. At this stage, the body is not experiencing a single failure, but a network of interconnected strain, hormonal imbalance, immune dysregulation, metabolic inefficiency, and structural degradation all reinforcing one another. And yet, even this is not the deepest layer of the system. Beneath cortisol signaling, beneath inflammatory activity, and beneath metabolic disruption lies a mechanism that governs the fundamental limit of cellular lifespan itself, a structure so central to biology that its discovery reshaped modern sense. That mechanism is the telomere system, and it represents one of the most direct biological measures of how cells track time and aging. In 1984, at the University of California, Berkeley, a molecular biologist named Elizabeth Blackburn and her graduate student Carol Greider made a discovery so unexpected that the scientific establishment initially resisted it. They were studying the ends of chromosomes, the protective caps that prevent genetic material inside every cell from fraying, fusing with neighboring chromosomes, or triggering DNA damage responses that would cause cellular self-destruction. These structures are called telomeres, and what they discovered was an enzyme, telomerase, capable of rebuilding them. This work would later earn them the Nobel Prize in Physiology or Medicine in 2009. But the more immediate and more unsettling implication of their research was this. In most human cells, telomerase activity is extremely low or absent, which means that every time a cell divides, the telomere at the end of each chromosome becomes slightly shorter. And when that telomere reaches a critical threshold, something fundamental occurs in the biology of aging. The cell enters a state called senescence. It does not die immediately. It persists. But it stops dividing and begins behaving in a fundamentally different way, one that is increasingly recognized as destructive to surrounding tissue. Senescent cells begin secreting a mixture of inflammatory molecules known as the senescence-associated secretory phenotype, or SASP, which promotes inflammation, degrades the extracellular matrix, suppresses immune function locally, and critically, signals neighboring cells to accelerate their own aging processes. In essence, senescent cells are toxic neighbors. They remain in place. They alter their environment. And over time, as their numbers accumulate in tissues such as skin, cartilage, muscle, blood vessels, and even the brain, those tissues begin to reflect their influence, becoming stiffer, less plastic, slower to repair, and less efficient in communication. And the organism itself begins to feel, in its joints, its energy, and its mornings, as though it is operating on an older biological timeline than its chronological age would suggest. But the research also reveals something crucial. Telomere length is not determined solely by genetics. It is dynamic. It responds to environment, behavior, and the biochemical context created by daily life. Large-scale studies have shown consistent associations between shortened telomeres and chronic psychological stress, poor sleep, high glycemic dietary patterns, sedentary behavior, and social isolation. Conversely, longer telomere maintenance has been associated with regular physical activity, diets rich in polyphenols and omega-3 fatty acids, mindfulness-based stress reduction, strong social connection, and a sustained sense of purpose and meaning. This reveals something both humbling and profound. The biological clock inside your cells is not a fixed countdown, but a continuous negotiation between entropy and maintenance, between molecular degradation and biological repair. To understand how this manifests beyond the cell, we turn to the nervous system, because it does not passively observe biological aging. It actively shapes it. The autonomic nervous system operates beneath conscious awareness, regulating heart rate, digestion, immune activity, and hormonal balance through two primary branches. The sympathetic system, responsible for activation and mobilization, and the parasympathetic system, responsible for restoration and repair. A body dominated by chronic sympathetic activation driven by sustained stress, sleep disruption, inflammatory load, and persistent threat perception is a body that systematically deprioritizes repair processes. Heart rate variability. The beat-to-beat variation in cardiac timing serves as one of the most reliable non-invasive indicators of autonomic balance, and consistently low HRV is strongly correlated with accelerated biological aging, cardiovascular risk, cognitive decline, and increased all-cause mortality. In this sense, the heart is not merely pumping blood, it is continuously encoding the state of the nervous system, moment by moment, reflecting whether the body is in a mode of survival or restoration. Beyond this lies the epigenome. DNA is not a static blueprint. It is a dynamic, chemically annotated system in which gene expression is regulated through methylation patterns, histone modifications, and chromatin structure. These marks change in response to environment, behavior, stress, diet, and time. One of the most significant advances in modern aging science is the development of epigenetic clocks pioneered by UCLA mathematician Steve Horvath, which estimate biological age by analyzing DNA methylation patterns with remarkable accuracy. What this research has consistently demonstrated is that epigenetic age can diverge significantly from chronological age. Some individuals exhibit cellular profiles that appear biologically younger than expected, while others show accelerated aging signatures. And this divergence aligns closely with everything previously described: chronic stress exposure, inflammatory burden, mitochondrial function, sleep quality, metabolic health, and cumulative lifestyle history. The epigenome, in effect, is a biological record. It encodes the history of the body's internal environment, translating lived experience into gene expression patterns that influence how efficiently the body repairs, regenerates, and maintains itself over time. Yet perhaps the most significant finding in epigenetic research is not its predictive power, but its responsiveness. Epigenetic states are not fixed. They are modifiable. Methylation patterns can shift. Mitochondrial function can be improved. Inflammatory signaling can be reduced. Hormonal balance can be restored. Autonomic regulation can be recalibrated toward parasympathetic dominance through structured evidence-based interventions. Sleep, when treated not as passive rest but as a biological priority, becomes a primary window for growth hormone release, autophagic clearance, glymphatic brain detoxification, and immune system recalibration. Exercise, particularly resistance training and cardiovascular conditioning, drives mitochondrial biogenesis, preserves muscle mass, improves vascular elasticity, and enhances antioxidant defense systems. Dietary patterns that reduce glycemic volatility help limit glycation and downstream tissue stiffening while providing bioactive compounds that regulate inflammatory gene expression and support cellular resilience. Stress regulation, not as elimination but as recovery capacity, strengthens autonomic flexibility and restores heart rate variability toward healthier ranges. And perhaps most significantly, psychological purpose, the subjective sense of meaning, has been consistently associated with longer telomeres, lower inflammatory markers, improved immune function, and slower epigenetic aging, suggesting that biological systems are deeply sensitive not only to physical inputs, but to cognitive and existential states. What this ultimately reveals is that the sensation you woke up with, that subtle but persistent sense that something feels off, is not random. It is information. It is the output of a complex biological system continuously monitoring itself across multiple layers of regulation, from cellular repair mechanisms to hormonal balance to neural state to gene expression patterns. And while that signal is imprecise, it is not meaningless. It reflects the current balance between damage and repair, between entropy and organization, between stress and recovery. The important realization is not that the body is in decline, but that it is responsive. It is adaptive. It is still actively negotiating its trajectory. And the question is no longer whether that trajectory can be influenced, because biologically it can, but whether the signal is being interpreted clearly enough to guide what comes next.